Hello everyone, welcome to Statistical Foundation for Big Data Analysis. So we are halfway through the course. We have covered 6 modules. This is going to be 7th module, and in this module we will mostly discuss the generalities of multivariate distribution. We have already seen in various cases, like we are in the ultimately we are trying to do for big data. So we are trying to do statistical foundation for big data, and the statistics needed for big data are practically always involves multiple random variables. So the distribution involves distribution of random variable in higher dimensional spaces. So the multivariate distributions give us the classical study of multivariate probability, gives us the probability theoretic foundation to that. We have already kind of encountered multivariate distribution on various occasions. For first lecture of this module, I'll just take a step back and quickly review some of the basics of multivariate distribution. Here is a reason for that. So the way this course will move on from now on, in this module we will discuss the basically one most important multivariate distribution, the multivariate normal distribution, in full details, and also focus on its special case, the bivariate normal distribution, because in case of one variable setup we have seen that if you collect a large IID sample of a large size, and you take its average, then that tends to behave like a normal distribution. The same thing happens for multivariate distribution also. If you take a multivariate random variable, if you take a multivariate distribution and draw a large IID sample of large size, if you take its average, under mild condition it tends to behave like multivariate normal distribution. We will define what multivariate normal distribution is. It also has this multivariate analog of this bell-shaped behavior. All those things happens, and this is extremely important because like univariate distribution, whenever we don't know anything about the pattern of the distribution of the population, as if you have large sample, we can approximately assume the average will behave some kind of normal and get some approximate inference, and this gives us a foundation gives us the foundation for dealing with multivariate random variable setup or the multivariate statistical setup. So in this first class we will discuss the generalities of multivariate distribution a bit. So random vector x1 x2 xn is with joint cumulative distribution f x1 x2 xn, the probability x1 less than equal to x1, x2 less than x2 xn less than equal to xn. Suppose you have a multivariate random vector, like you have a random vector with this f being its joint probability distribution, then the following properties hold. Just to view, we have already defined cumulative distribution function and probability density function. We have defined already CDF and PDF. Just to review some of the properties of those distribution theoretic objects in multivariate. So this has to be monotonic. For one variable, if your density is something like this, whatever, doesn't matter. The fx, if this is your fx, is the probability of this portion. Of course, probability of this portion is some non-negative value. Now if you take x plus some z, this portion, the probability of this will be probability of this plus this. So obviously it is a probability of a bigger set, hence it has to be non-decreasing. Same thing goes for this. If you have x, just to visualize in 2 dimension, if you have, this is your x1 x2 and this is your y1 y2. So y1 greater than x1 and y2 greater than x2 simply means the point y1 y2 is both above and on right of x1 x2. Then the density at this point is just the probability of this region, and density of this is of this region which contains this extra region. So you will get this property. So one technical condition we always need, I kind of ignored some mathematical nitty-gritties, but it's better to remember at least that it is from calculus point of view, it's continuous from the right with respect to each coordinate variable. We will not need this in this course that much because most of the thing we will get will be very smooth and nice functions, but it's just, you know, for it's just, you know, good to know this as a fact that this density function is continuous from the right. It need not be continuous from the left in general. Some boundary condition, if any of the xi goes to minus infinity, just from 2 dimension, imagine for any value of y, if x is going to minus infinity, so this is your x, so suppose y is the height, this is your xy, this is the probability of being less than or equal to xy. The thing is, if you make it go to infinity, if x go to minus infinity, you are getting this, so the probability is starting to get smaller and smaller. So eventually the space will be empty, so the probability will be 0. And if all x's go to infinity, so then this will start getting bigger and bigger, so it will eventually cover the whole space, so the probability will be 1. So this quick geometric patterns, it will be good to remember this when you are dealing with multivariate distribution. So when you are trying to calculate probability of this portion, I mean this complicated, you know, looking formula involving, you know, this alternating sum, essentially says you want the probability of this portion. So to find probability of this portion, you first find the probability of this large portion, call it A, then subtract the probability of this portion and this portion, call them B and C, but you have subtracted this probability of this portion twice, so you add that, call it as D. The point is, you want to express this expression, the probability of belonging to this region, in terms of the CDF function itself. So if you want the probability of this box, that, you know, x1 belongs to this region and y1 belongs to this region, that this box here is this giant half plane minus this giant half plane minus this giant half plane plus this, and all these 4 things are f for something. So you can express this probability of this, you know, this falling in this region in terms of these f probabilities. So if it is, you are talking about discrete random variables, so it's just essentially the setup where you can assign probability to points in various different points, and the probability of any set is sum of the probabilities of the points belonging to that set. So basically, if you have discrete many points in Rn, such that you can assign probability to each of those points. So Pi1, I2 dot 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 In is basically the probability of x1 taking value x1 I1, x2 taking value x2 I2 dot 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 xn taking value xn In. So you will get discretely many points in the space where each point will assign one of these probabilities Pi's, and then when you are talking about probability of a particular set, you just take the sum of those probabilities. So this is basically, sometimes it's called jump at that point. You're, you know, when you're comparing with the density like the PDF, it's sort of it's smooth. So, you know, just imagine the one-dimensional picture. When you are talking about density, you just integrate some nice looking function like this, whereas when you are taking discrete, you kind of have probability values like this. There, if this is f, the integral f is 1. Here some of these P1, P2, the sum of the Pi's is 1. So this is sort of a smooth kind of object, and here these are kind of discrete jump like object where total thing of that gives you 1. So clearly summation of the all the probabilities, total probability has to be 1. When you are talking about this discrete setup, when you are looking for cumulative distribution function, it's just the sum of all the pi1 i2 in such that the x1 i1 is less than equal to x1, x2 i2 is less than equal to x2, and xn in is less than equal to xn. Clearly, so if you're basically, if these are your discrete points, if you're looking for this, you just take the sum of all the points that falls in this region. So, and this p i1 i2 in, this is called basically the joint probability mass function of this random vector x. So this is an example. You have rolled a fair die and tossed a fair coin. If this is the face value on the die, and if y equal to 0 if you get tail, and y equal to 1 if head turns up, then you basically get all these possibilities. You know, the first 6 are the tails for the toss of the coin and the various values for the die, and the second 6 are the heads and the various values in the faces. These are all independent. For getting a particular value for the rolling die, probability is 1/6, and getting head or tail is half. So each of the pair has the value 1/12. So this is basically an example of a probability mass function in the bivariate setup, special case of multivariate. So this is a simple calculation of the whole CDF, CDF function. So basically, if x is less than 1 and y is anything, there is no, x is the value in the die, it cannot be less than 1. If x is less than 1, whatever y, it is 0. If x is between 1 to 2 and y is between 0 to 1, it is y is less than equal to 0, greater than equal to 0, and less than 1 means y equal to 1. So this means y equal to 1 basically. These are all y equal to 1 cases. These are all y equal to 1 cases, and these are all y equal to 0 cases. These are all y equal to 0 cases. So you can calculate the CDF using just sum of the probabilities of points that belongs to that region. So in case of continuous random variable, as we have seen, there exists a probability density function whose integral over a particular set gives you the probability of the vector belonging to that set. CDF f x1 x2 xn is just merely probability of x belonging to the region where x1 belongs to minus infinity to, so capital X1 belongs to minus infinity to small x1, capital X2 belonging to minus infinity to small x2, dot dot dot, capital Xn belonging to small xn to minus infinity to small xn. So you integrate this function over that space. Here also basically, if you want a probability of the whole space, you just take all the xi's go to infinity and probability of everything will give you 1. So this is one important property of this PDF. Now, when you want to define marginal PDF, so basically from the joint distribution, if you want to find the probability of each random variable taking a fixed value, now this is a random vector, so this is random vector and each of these are random variables. So each of these takes individual real values. So if you want from here, you want to calculate the probability of xk taking, capital Xk taking value small xk ik, you simply add up all the p i1 i2 ins where basically all these things, all the other things basically, you basically add up the values where xk is taking the value xk ik. And so whenever you want to basically calculate the probability, if you have a joint distribution of x1, x2, xn, and from there, suppose it's discrete type, that is probability of x1 taking value small x1 i1, x2 taking value small x2 i2, xn taking value small xn in. p I1, I2, In, when you are trying to get the probability of xk equal to small xk ik, you just fix the value of xk at small xk ik and take all possible combinations of values for the other random variables and add all the sums. So basically xk probability of xk equal to xkik is nothing but xk equal to xkik and all other xi I not equal to k can take any values. So you take all possible combination of values for the other random variable and keep the value of xk at xkik and take the sum. That's how you get the marginal PDF for the discrete case. And in the, so this is one example where you are taking basically fair coin is tossed 3 times, x is the number of heads and y is the difference is absolute value between number of heads and tails. This is your joint distribution of x and y. From there you can calculate the marginal distribution of both x equal to x for various values of x and y equal to y for various values of y. Now for same thing goes for the continuous setup. If you want the marginal PDF of a random variable, you just integrate the all other random variables from minus infinity to infinity, keeping that one fixed. So when you want fk xk, you just integrate the joint PDF f x1 x2 xn with respect to dx1 dot 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 dxk minus 1 and then dxk plus 1 up to dxn. So this is dxk missing as xk is fixed. So you are keeping the xk fixed, the xk value fixed and integrating everything else out. So basically probability, so densities are infinitesimal probabilities. So it is essentially kind of saying infinitesimal probability of xk taking a particular value is basically probability of infinitesimal probability of xk taking that value, and if the other things can be anything. So you can just integrate out other random variables from minus infinity to infinity, basically sum over all possible values of the other random variables. Whatever you get, that is your infinitesimal probability or density of xk. So this is an example. If x and y be jointly distributed with PDF fxy equal to 2 and when the x is xy both takes value 0 between 0 and 1 and x is always less than 1, you can basically see the when you want the marginal distributions, you can integrate out the this fxy. So if you want marginal distribution of x, then you just integrate the whole y out and then for fixed x, but then for fixed x, y will vary from x to 1. So basically that gives you 2 minus 2x for all x between 0 to 1 and 0 otherwise. And similarly the marginal density for y also can be calculated. So this is the area where fxy takes value 2 and 0 outside. So for multivariate conditional probabilities, when you want the conditional distribution for xi taking a value given yi taking a value, you know from the definition of conditional probability, this is just the probability of x taking value xi, y taking value yj, and you divide by the probability y taking value yj. The same thing with the interpretation of density being infinitesimal probability can be applied to conditional density. Conditional density of x given y becomes basically the joint density of xy divided by the density of y. So for the joint PMF of coin toss example, you can calculate the probability of x taking value I given y equal to 1. So more or less a simple discrete calculation, not spending too much time on this. So in case of multivariate case, when you are talking about conditional expectation, see, I am not spending too much time because these things I earlier also I kind of did. I am just quickly reviewing this. You can please carefully take a look at the calculations. So for conditional expectation, we talked about it quite a lot in statistical learning theory. Just to remind, the expected value of x given y equal to y is basically the average of x with respect to the conditional distribution of x given y. In case of discrete, it will just be sum, and in case of continuous, it will be just integral of x with respect to this conditional density function. So if the function, so basically this shows basically you for conditional expectation of y x given y equal to y is a value. That value depends on the value of the y, so it becomes a function of y. We saw this using this iterated formula that conditional expectation, we know that expected value of, we saw this and we heavily use this expected value of x given y is actually expected value of x. We saw this quite a lot when we were discussing bias, variance, etc. So, some properties of conditional expectation. The conditional expectation also preserve linearity, as we said, law of total expectation. Conditional expectation gives you the unconditional expectation back. If x and y are independent, then conditional expectation of x given y is just expectation of x. Basically, for if x, y are independent, conditional density of conditional distribution of x given y is just the distribution of x independent, irrespective of whatever the y value. So basically, so this is basically here you will be integrating x with respect to f x y dx, but this is nothing but fx, and same for discrete. I mean, the integral will be replaced by sum, hence this will just be integral x fx dx, which is just the expected value. So function of conditional distribution. So if you take basically a function of y, well, if y is given, for any function of y the value is fixed, so it just becomes something which is non-random. So expected value of a constant is constant. So for any function of y, hy, conditional expectation of hy given y is just hy. So these are some examples of conditional expectations, etc. This is back to this example. I think we did this example before. I'm just reviewing once more. It's the same fxy we just saw a little earlier. The marginal distribution of f, the distribution of y is just 2y for y between 0 to 1. The conditional distribution of x given y, the conditional PDF of x given y is the unconditional divided by the marginal of y, which becomes 1 over y. So when x between 0 to y, so this shows basically x given y equal to y is basically uniform 0 to y. So using this, we can calculate the expected value of x given y equal to y. For the uniform distribution 0 to y, you know the expected value is just the midpoint. So this is exactly what you are getting. Finally, using the same setup, you can find the expected value of x. Expected value of x is expected value x given y, expected value of expected value x given y. So it is expected value of y over 2. 2 is half, it goes outside. We have seen we have found the PDF of y. So you just use that PDF to find the expected value of y, which is just y times 2y, that's a PDF, dy between 0 to 1. So that comes out to be 2/3. So expected value of x will be basically half times expected value of y, which is half times 2/3, 1/3. So this is just a very quick, almost like a blitzkrieg overview of multivariate distribution and multivariate random variable. Many of these have been used before. I'm just giving you, it's not possible to give a completely exhaustive exposition to probability, because we kind of use probability as a backup. I'll just give some references from where you can read about conditional probability and conditional distributions in detail. Thank you. I stop the class here.